it's on there. Just waiting for confirmation on the YouTube end. Hey, we are live. So uh, I will quickly share the link on Twitter and then you can begin. No, we can do that later. Hello everyone to another Open Hours. This time we are finally back live on YouTube, and we are with a very special guest. We have our team from AiSing, and I'll go a bit more into detail about them and introducing them. But first, I have a few links to share. Uh, we are broadcasting live on YouTube, and this is a odd time for our regular Open Hours viewers. So we will be rebroadcasting this on our regular time at 4 p.m. UTC. So if you can't catch it now, we'll do that later as well. And I am going to share a link to a couple of pages where you can find us. We are available on Twitter at 96Boards, and we are also available on Discord. So all the updates of stream times, etc., are available there. So just copying this over to Twitter as well. All right, so I welcome our guests from AiSing. They are AI venture established during 2016. They're well known for their deep binary tree AI algorithm, which is very much geared towards edge devices, and it's actually pretty darn fast if you look at their prediction times, which is around 1 to 5 microseconds, and learning time of around 0 to 100 microseconds or 10 to 100 microseconds, and all of that running on a very basic device such as the Raspberry Pi Zero. And lately, and the reason we have AiSing on the call is that they've been working with more powerful SBCs like the 96Boards IK 960, and we really hope to learn a bit more in detail later during the episode. So we'll actually be going through a couple of topics, including their AI real-time technology and how customers can utilize AI. I would now like to hand over to Masa from AiSing, and I would like him to introduce AiSing a bit in a bit more detail, and maybe also introduce some of his teams, and then we can go into the presentation, and then we'll have a Q&A towards the end. So all the questions you have about the technology, you can keep writing it down, and we'll do a session later once the presentation is over. So, Masa, over to you.
Okay, thanks, Saha. And hello, everyone. My name is Masayoshi Tanaka. I'm a senior researcher of R&D department. So let me show my screen sharing. Okay, can you see this?
Yeah, I can see it.
Okay. So today I will talk about AIR. It's a short of AI in real time. So I will introduce our core technology AIR and some application process. So at first, today I prepared two topics. One is introduction of AI itself, and another one is a consideration about development of edge AI. So because so to develop Edge AI, it is necessary to make some kind of the collaborative development style with customer. So I hope this kind of the information will some kind of help to develop MCU board like 96 board. Okay, let's start from the first topic. So first of all, I will introduce about our company profile. So AiSing is a coined word that stands for AI and singularity. So, and we have founded in 2016 and located in Tokyo, and established as an industry academia collaborations company with Iwate University. So we already invested $9 million this year, and providing our original Edge AI solution. So that's the point is we have only provide a software engine or software solution. We don't sell actual hardware like MC board or chip or something like that. We are focusing on the software IP business. So yeah, as you can see, AI is a short term for AI in real time. So that's a point for real time to utilize about real time embedded system like a machine control or something. And also we utilize various machine learning engine in their solution. And all of the software works on the ordinal MC board. That's important thing. So before the detail, talking detail about AI, so I will mention about some trend of AI industry. So today, so many companies tend to deal with AI business. So, but every company has a different aspect for each business. But I find some trend, a big trend, is movement from cloud to edge device. So several companies wants to make power up edge device by using several technology like Google Edge TPU. It's ASIC style specific ASIC chip is released from Google. And the second one is, it's a 96 board regression. So Xilinx FPGA is implemented on the MC board. And the third one is NVIDIA's GPU accelerated MC board named Jetson. So all this technology is based on deep learning by using neural network processing. So basically, a deep learning system is consuming a huge computing resource. So everyone can feel so such kind of special hardware is necessary to reasonable performance to be as a edge side device. However, the most of the embedded system is so kind of the very sensitive for the cost increase. So product design engineers in manufacturer is making significant efforts to reduce costs. So it's natural to wonder the increase of cost is worse or not. So AiSing is approaching in different way. So to providing a lightweight AI engine, and it's not based deep learning. So tree-based algorithms is adapted. And also focusing on the machine control. So as a result, so all of the AI capability of learning and the prediction and updating learned model, this works on the ordinary MPU or MCU board without any extension hardware. So I think there's a big difference between the tree-based AI and deep learning in characteristic and the suitable application. So for example, the image recognition or action planning is not suitable for the tree-based small system. But we focus on the machine control business. So by focusing on this, so several characteristics is make a big profit for us. For example, the computing cost is drastically low, and explainability is very high. Learning speed is fast, and also we can provide online learning. So online learning is the most important, one of the important factors of our system. By using online learning, so learned modern data can be updated during operation. That makes a non-stop operation for the AI system. So by using this functionality, you can hide the bad effect of aging or individual difference or environment changes. So for the different sites, so ordinal deep learning system is categorized in batch learning system. In this case, so updated learned model is a zero-based from scratch. So it means all of the learning data is necessary for the new learning. And also it takes a very long time. So, so it's not a real time working to update learned data. So for our system, so let's explain about suitable application of our system is optimization of controlling and anomaly detection, the future prediction, and reduce wasting, something like that. And also business category is one is a factory automation like industrial robot and productivity line, and by using a PLC is a programmable control, programmable logic controller. And also mobility devices like some train control, train investigation, or kind of the car controlling system. But that's a slightly different of the focus because we don't handle, we will not handle about the automatic driving system. So we focus on the more small or partial controlling system like braking or anomaly detections, like that. The third category is facility management, like air conditioning system of the huge buildings, or heating system, or so any power plant, something like that. Okay, in the second, in this page, you can see the development history of our development. So in 2016, we developed our first version of deep binary tree. It's based on collaboration with Iwate University. And after that, in last year, we released improved version of DBT. One is a DBT high quality, and another one is a DBT high speed. So these two learner is cover more wide coverage for the high quality requires a rich resources, but the result will be good. And last week or 2 weeks ago, we will made a press release about the new machine learner of SARF. It stands for self-adaptive random forest. Random forest is a tree-based, very common AI algorithm, but we improved by additional learning. Oh, that means online learning capability to random forest. And furthermore, now we are trying to develop more and more new kind of learning algorithm. Let's take a look at the comparison chart of our machine learner. So up to learner, we already have released to the customer, and SARF is just preparing to release. And the bottom one is still under development station. So you can see the memory footprint is very varied by the requirement of the customer. So, but in this simple cases, learned model size is 10 megabytes or so. It's not impossible to implement a very small embedded MCU or like that. And all of the learner can learn at the edge side and also learn additional learn or online learning is available. But so in this chart, it's very hard to understanding how is the actual computing cost. So I described in the next page. So DBT HQ and DBT HS is coverage for the processors type is kind of the, so Intel is kind of the top level performance, and Cortex AX will be a second part, and DBT high quality is covered for the Intel and Cortex AX series, but lighter algorithm DBT HS covered also Cortex M7 with SDRAM. So that means calculating cost is very low, but model data is not so small. So it's necessary to use SDRAM to allocate a big learned model. However, so now we are developing more and more lightweight solution. So in that, after that, so maybe Cortex M series without SDRAM will be available for our AI solution. So you can find high-key 960, and also right side STM32 evaluation board will be published the press event or conference for the exhibition demonstration. So last year we took press conference for this DBT high quality. So at that time, so high-key 960 has introduced as an implemented platform. So you can see the one of the Japanese web news site. In this report, you can see the our CEO Junichi shows the high-key in his hand. Okay, that was an overview of our solution. So now we move on to the next topic here. So how to develop edge AI system? I think it's not easy way because AI is embedded element, so it doesn't work standalone. So our business is not like that just selling a package software application. So it required many collaboration with our customer. So it needs many testing, evaluation. So after the so many iteration of the evaluation, maybe final answer will be defined. So to make this, I will explain about the typical development style. Actually, development style or workflow may differ for every customer, but the definition must be done beforehand. I think it's like a generic development style. Yeah. After that, we have development sequence will be divided into 3 steps or generic board. And the second phase is a prototyping. So in this phase, we verify feasibility. So is it works in a real-time system by communicating with actual target machinery? The third phase is mass production. In this phase, we must implement with mass production level, cost, and quality, and also productivity. So I will break down for the every phases. And first phase, POC working may works at the customer side. In that case, customer can use evaluation PC working with AIR module. AIR module is a hardware, external hardware, including AIR firmware with IP protection, and a standalone board or enclosure module will be available. So today we only release high-key 960, but unfortunately, some of the customer don't want to some kind of the so controversy between the US and the Chinese issue. So don't want to use a Chinese-based SoC system. So now we are checking the alternative for the high key. One candidate is Armaggio. It's a Japanese company's product by using NXP's SoC. In this phase, so important point is easy to use. So in this phase, customers don't want to develop hardware. So just gathering commercial hardware, it will be necessary. And to the next phase is prototyping. In prototyping phase, host system is almost same as a final production system, and also can be communicated with target machinery, and also communicate with the air module. Air module side is almost the same as a POC phase, but it's required to work in real-time system. It's just difference between the prototyping and POC. In third phase is a final product in manufacturing level. So air functionality should mounted on customers PCB, not external module. This will be theoretically best solution. So, and also as I mentioned, so AiSing doesn't handle any hardware. So we use the commercial SOM and embed their firmware into SOM and provide to our customer. So just summarize the three phase hardware variation. In PLC phase, standalone air module plus PC. In prototyping phase, air module plus customers prototype PCB. And in mass production, air SOM and production PCB. So requirement for the air module is different for each phases. So, but so to realize this, so there are several problems. Problem number one is a cost problem. We should serve many kinds of machine learning core engine, and all of these should work on the various MCU and should support for various connectivity. So if we develop all of these in straight way, it makes a kind of explosion in development cost. So it's necessary to reduce the development cost for to realize many choices. Second problem is impact of specification changes. Requirement for the hardware may change according to the development phase, and also by result of test and evaluation working, maybe causes some change of specification. For example, the MCU power is not enough to our system, so we need more powerful one. Or communication is too slow, so we must change to a faster communication method. Will be some typical cases. So, and also it's necessary to reduce the impact of specification changes. So to clear of these two problems, we have developed a common framework for AIR. We call that AIR framework. So this framework is not depends on the kind of machine learning system in the other systems. we have split it in software into 4 sections. One is a machine learning core itself. And another one is a command interpreter system. The third one is a communication system. And the bottom one is a hardware abstraction layer. Covers the difference between the different type of the MCU or OS or system level management, like hardware initialization or memory management. For each sections, we provide some plugin module. For the ML core section, we have developed a DBT-HQ module, DBT-HS module, and SART module, like that. And also, we have developed for the communication section, UART module, or SPI module, or TCP/IP module. So by using this communication section, so customer can use a different communication style or session management in the same way. So important point is so red arrow describes a intersection API. So we define the rigid common APIs between the different sections. So by using this, so if the one of the section is replaced with a different module, so overall architecture will be the same. And also we have prepared as a hard HAL layer, so STM system or NXP system or Cypress or Renaissance or will be developed in this section. So by as a result of introducing AI framework, for example, in case of that, the customer must support a brand new hardware or specific board. So in this case, you can only develop hard module. And also, so by request changes for the different MCU type or memory size or connection method, it's still, you can still use the same command set or same libraries for the customer program code. So I explain about the basic concept of AI framework. However, the AI framework itself is just a software solution. So I think the same consideration is occurred for the hardware side. So then I will explain about my consideration for the hardware. It's not actual result of investigation, but my personal opinion for the in the current situation. So one is how can we make a variation of hardware? So typical solution for this case is carrier board style. To make a final product, SOM style, very small SOM style is suitable for the final product, and that have a PCB interconnect to customer PCB. But in the phase of POC or prototyping, so user wants to use a standard connector like DSUB or RJ45. So carrier board will be useful for the POC phase development. But also, it's also okay to use a compatible board in the seamless, simple MPU or MCU board directly mounted on the SoC or external RAM or flash RAM. So, but it's important point to so in the if the hardware style will be maybe different, so but the user program or air solution firmware can be works as single code should be work on the different hardware style. So compatibility is very important. And also to talking about consideration of SOM. So how to reduce the cost of SOM. So final products requires wants to use minimum connectors because the communication between air module and customer's PCB is very simple, like one single UART serial port or one single SPI port. So extra connector doesn't require for the customer, but the extra connector increases the total cost. And also, so memory size and clock speed. So if the customer's requirement is very simple and a simple learn model or less data, in this case, so less memory or slower clock is enough to use the as a SOM. Overspec is raises cost. It's also a problem. So, and the second point, I already mentioned about compatibility problem. Compatibility between final product and POC prototype is very important. And also, not every customer can develop original MPU board. So in that case, so very simple carrier board style is also useful for the customer. So I briefly just summarize today talking. So for the to develop edge AI, so requirement from customer may vary for the collaborative development style. So it's necessary to have various choices of hardware or communication style. And consistency in different choice is also necessary. And how to make this subject, so air framework makes it already solve the problem. And also flexibility of SOM will be helpful for to develop edge AI device. Yep, that's all for the today's my presentation. Thank you for listening. So, any questions or discussion?
Yeah, I have a lot of questions now. Thank you for the presentation. It was amazing.
Yeah.
A lot of new things about like AI, a very different approach to AI for it, like being very real time. I was also sort of reading another one of your on your website where it says I think up to 10 seconds of prediction, up to 3 seconds or 10 seconds, and that's like a very different approach to AI from what we see being done um, like by most people. It's like everyone wants to predict much further down the road, whereas yes, in any sort of real time application where you are, let's say this is something that's um, implemented in something like a hypercar, right, where you need to constantly adjust your aerodynamics, you need to constantly adjust your downforce and stuff like that. uh, or similarly on a fighter jet where new age jets are imbalanced by design so that they can be agile, and you need to constantly keep on adjusting. And in those applications you don't need to look uh, an hour into the future. You just need to see what's the condition going to be in, say, the next 3 seconds, the next 5 seconds, and very quickly adjust for optimal performance. And that's sort of what I am seeing here, where you can replace the old type if else statements and that sort of a program with an AI of this sort, where it can just constantly keep on updating its model according to the conditions, and just adjust everything in super quick, like real time environment.
Mhm.
So that is sort of what I've learned from this. And yeah, I do have a lot of questions. So earlier I was going to ask whether do you support MCUs. Then you do clear up that DBTHS, starting from DBTHS, and there will be support for it. I'm very interested to know what sort of firmware you are running on MCUs. Is it over some sort of RTOS, or is it bare metal code?
Sorry, could you repeat again? Could you repeat?
Yeah. So, are you using something like FreeRTOS as a base real-time OS, or
Uh,
are you just writing bare metal code directly running on the Cortex M?
yeah, okay, I understand. Our process is independent from OS side because just calculation. So it doesn't require the specific system call like that.
Okay, that clears up the yeah. So I saw that, and the first thing that came to mind with running it on the MCU is then my sort of um, my sort of understanding of how a board like we have our Avenger 96, and this board is powered by the STM32 MP1, and it's the amalgamation of dual Cortex A7 cores and one quite powerful, quite high clocked Cortex M core. And the thought always was like the heavier AI-ish or learning task can be offloaded to the A7 core, but there's now the possibility that it's the opposite, where in specific use cases, my Cortex M core is actually always on and doing the actual AI. And if there is a trigger event, it can turn on the A7 core if required. So, have you tried on devices like these? There, I think IMX 8s and 7s as well that have the Cortex M and A cores integrated. And I think the major advantage here is that on such devices, the DRAM is shared. So sometimes you can get huge amount of DRAM available to the Cortex M cores.
Yeah, I think that most of the station, so the bottleneck is just memory size. So computing cost is not a bottleneck. So maybe, for example, the IMX8 will be overspec.
Yeah, no, right. The IMX 8 will be overspec, but if you only run the AIIR, the
Mhm.
AIIR stuff on the Cortex M core on the IMX8, and you allocate enough DRAM to it, then it might be worthwhile.
Yeah.
And then you can have something more compute intensive running on the A core, which stays in like a sleeping or hibernated state and only wakes up
Ah,
when the Cortex A core says, "Hey, I've done some real-time AI stuff. I've detected a particular event, and I need you to wake up and take some action."
mhm. Yeah, that makes sense. So for the how to make mm, calculation cost impact for the customer. So basic performance, higher basic performance should be better for the customer. It's clear. But and also many cores SoC. will be also a good solution for well, so for example, the one single core of the multi-core system is occupied by, for the air is one idea for the shared resources between the our for us and the customers.
So also another question, I think you already talked about it, but is this can this be used completely offline? There's no network connection, there's no cloud connection, and this is just running on its own.
Oh, so sorry, I couldn't catch that.
Uh, so does this actually run completely offline? Like if there's no internet connection, there's no connection to any sort of cloud.
Sure. We
Yeah.
don't need any network connection.
Uh, the other one is something a bit more interesting on my end.
Hmm?
How complex can the input data be? Is this only geared towards basic sensor
Oh,
data, or can I go
mhm.
to like low resolution camera or some LiDAR input as well?
Yeah. Basically, the dimension of input data should be less than 100. So that means image data cannot be handled for the solution.
But if you get a very low resolution LiDAR, that
Yeah.
might
Yeah, maybe okay.
okay.
So, and also, uh, basically, so we handle double precision floating point. So,
Okay.
precision maybe it is not be a bottleneck.
Okay. Yeah, that makes sense. You did say that you are using SOMs for
Mhm.
the intermediate development stage, and even in some cases, if the consumer cannot expense their own boards, that SOMs go into final production. Um, I now need to tell you about 96 board SOMs. So 96 boards actually has its own SOM spec.
Mhm.
I will
Yeah.
just share the image so everyone can see. Let's see if I can screen share. Um, there you go. And here you can see this is our main page. We have our SOM edition. So this is sort of our ideal baseboard, and yeah, so we have two basic SOM specs SOM modules that we use. One of is a full-sized one, and so that gives you a lot of interface like PCI, high-speed USB, uh, and stuff like that, and that sits on all four of our SOM connectors. But there's also like a smaller SOM spec uh, that sits just on the two connections here, so you can see it's not covering all of the board. And this particular module is more low speed stuff, USB to doesn't do PCI and USB and UART and networking and stuff like that. So I just sort of wanted to put this out there that yes, 96 boards also has some specification that you guys might be interested in taking a look at.
Yeah.
I will um, actually add a link here in a second. Second. That's it. Yeah, so I'll add a link in the chat, and that's where people can look at sound specs as well. So that is also something very interesting if we can work together and support some of the pre-existing songs we have. Uh, so talking about Heike 960, I wanted to know how your experience was. Ouch. Uh, Hello. Um, did everyone hear that?
Just you.
Oh,
Hello, Mas, are you there still?
uh, I have no problem.
Okay, yeah. I don't know. I heard a very loud beep that almost like my ear is still hurting from that. Yeah. So I was asking how your experience with the IK 960 was.
Yeah. So for the using high key 960, I only have experience to use high key 960. So basically, the ALS connector is helpful for us because of the simple I/O is gathered on the ALS connector is very useful density. So because of high density connector is to use a high density connector, so conversion PCB must be required. So that's a kind of messy work for us. So ALS connector will be helpful, but the actually, so 2.0 millimeter pitch is slightly difficult to handle.
Yeah, we actually have a mezzanine. I have one
Oh,
here,
yeah,
and so this is something we use a lot around here because the 2.0 mm pitch was more designed because we have the 1.8 volt spec,
yeah,
and that's a voltage level that all SoCs work at normally, and on other boards that work at 3.3 volts, they usually step it up internally with voltage shifters. So we decided to go directly with the 1.8 volts, and I think the 2.0 spec was made because of that, also to save some space on the board, but mainly because that fits very nice with the 1.8 volt
yeah,
application.
yeah, I
So
understand.
we have a couple of boards that do level shifting, but I think the more full-fledged one is called the audio mezzanine. It is sort of geared towards the 410C, but you can actually remove the one header on the underside. So like I have removed it here, and then what you get is like uh, you have a bunch of level shifters here, and this is your two
Ah, I
inch
see. Okay, yeah,
2.5 inch, um, and then not inch sorry, 2.5 and then here you have a switch for level shifting between
mhm,
3.3 volts and 5 volts. So that's what the output level of this header would be, and this
mhm,
header matches the smaller header exactly.
yeah, 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 yeah.
So in this way you can actually get some of the peripherals to work very
Oh, that's
neatly.
good news. So level shifting is very important. So
Yeah.
by connecting converter hardware, so level shifter was one makes one problem, one trouble.
Yeah, it's been interesting to shift from 3.3 volts or 5 volts to 1.8 volts for us because most of the SBC industry has always stuck to the
Yeah,
3.3 volt level. And it's funny because if you take a look at something like the Raspberry Pi that uses 3.3 volts, they will, I think Pi still does it natively on the sock, but there's like no SoC out there that you can buy that does 3.3 volts natively on the IO. And a lot of other Pi clones that you see that do 3.3 volts, they like level shift it. So if you add a sensor to those SBCs, it's like the sensor is also designed for mobile application, um, and that runs at 1.8 volts. So they are shifting it to 3.3 volts on the sock and then shifting it back down on the actual sensor board back to 1.8 volts. And we just wanted to to do away with that. So some of our other sensor boards, we have a nice Bosch sensor Mizni that has native Bosch sensors on there that do 1.8 volts, and you can see like there's no chip on there apart from like say SPI bridge or I2C breakout and stuff like that. There's like actually no chip on there because there's apart from the actual sensors, because there's no level shifting that we do that we have to do. So yeah, that's a small story about why we use 1.8 volts.
Yeah.
Um, yeah, so I am going to actually open up the floor to our attendees at the moment, and they can ask questions. There are 15 of them, so please do ask questions. Feel free to open up your mic or ask on the chat. And if not, I will call you all one by one.
Yeah.
So hi, Masa. This is Joyce. Thank you for sharing your document. So I have some questions. So first, do you have some real example of your AI algorithm used in the factory automation?
For the actual application?
Yeah, I mean, do you have some real product using the AI algorithm already?
Yeah, not yet, but the some company have actually planning to adapt to for the production product. The name of the company is Omron. We have first make a press release last year or 2 years ago. So with a collaboration with Omron. So the PLC, the serial model of PLC will implement DVT-based solution into their product. Maybe next model or next. So I don't know the actual release timing, but now they are planning to implement to product.
Okay, I mean, yeah, that's very good. We're expecting to see the end product as soon as possible. So, I mean, for different use case, I mean, for some factory, for example, the vision detection or some different use case, maybe the platform in the different performance, right? For example, Cortex M, some user case need the Cortex A, and some AI accelerator. So what's the, because you have a software stack, you have a how, so how long does it need for you to integrate your AI algorithm to different platform?
Yeah, okay. So my newest experience to implement the new hardware is it takes about 2 weeks.
Oh, that's very fast.
Yes.
So what's your business model? If there's some other AC vendor or some end customer want to use your algorithm, how about the business model?
Actually, I'm not a business person, so I am not suitable to explain by that. But our business model is based on a license base. For example, loyalty or per product or gross payment. So NRE payment. So gross the combination of these elements will be a basis of our business.
Okay, so do you have some demo to show the customer what's the benefit or what's the comparing to the other AI algorithm? I mean, and before they select, they may want to see some demos?
Mm, ah, so the choice to choose the suitable algorithm is very difficult for the customer actually. So in the POC phase, so maybe the AiSing will have initiative for the to make a result. So AiSing side, so evaluation of the different algorithms or different parameters to make to clear the requirement. Is that okay? Is that answer
Yeah.
for you? For you?
Yeah, thank you.
All right. Let's see if anyone else has any more questions. Robert, Tayat, Victor, I see you guys there. You have your mic on mute. Uh, and anyone on the attendees list, you can raise your hand if you have any questions. All right. If not, then I think we can call it a day. It was, I think we managed to keep the time of 1 hour, and thank you so much for everyone for attending, and especially Masa and others from AiSing to be there with us on this call and answer our questions. We will be in touch with you, and of course, again, I am going to rebroadcast this call later on the actual open hours time at 4 p.m. UTC today. So there will be more questions coming in from that crowd as well. So Masa, I will be forwarding those questions to you, and hopefully you can answer that over an email thread.
Yeah, thank you today.
Yeah. And so I will be closing this out now. Thank you so much, everyone, for watching. And I will see you all in the next Open House episode. Again, once again, thank you so much for AiSing for this wonderful episode, and we'll see you all in the next one. Bye. And
Bye.
let's see.
Bye now.
YouTube. Bye, YouTube.